So in this case, I'll give a brief summary of what you guys want to cover to cover the syllabus point about chromatography. So the first thing is about the concept of the stationary phase and the mobile phase. So we briefly discussed it in terms of the size exclusion chromatography, but ensuring that you guys know what it means in terms of TLC and HPLC as well. Those are always important to know. So this is a core concept of chromatography as a whole. The next thing is the RF values. So you can see that they've briefly mentioned in this question about RF values. So it's important that you guys know what RF values are and know that this is specific to TLC, whereas retention time is the one that's important for HPLC. So I'm putting that distinction there, as well as what they mean. So in terms of what when I mean when I say what they mean, essentially what what does it mean in the context of answering a question in terms of interpreting data, for example, in this case, like what does the fact that these two are equal mean on the same level? What does this mean? And what does this mean? That nothing is really equal to that. So, what do these certain values mean in terms of the chromatography to interpret the graph? So, make sure you guys go over the TLC, HPLC a little bit more in detail so you understand what's going on. So you guys probably have, a somewhat good background from last year's chemistry about chromatography. Just make sure you guys just go that extra step to understand the differences between those two. So, in short, essentially, the chromatography that's mentioned in your syllabus is just essentially how different substances in a mixture or a sample just interact with that stationary and mobile phases, right? And then how you can use to separate and then identify and then analyze those substances using that RF value or that retention time, right? So that's basically a brief summary of what you guys want to know for to cover the syllabus point. So make sure you guys go over that, do a few questions just to understand what is going to be covered. All right, so let's get straight into mass spec really quickly. So here I've copied two of the QCAA syllabus points that are relevant to mass spec, specifically in the Unit 4 section. So keep in mind that mass spec is also covered in Unit 2, Unit 1 and 2. So just about, how it works, how the mass spectrometer works and everything like that, which I will be still talking about today. But that's grade Unit 1 and 2, so grade 11 stuff. So this is grade 12 and Unit 4 stuff, which is select and use data from analytical techniques, including mass spectrometry, X-ray crystallography, and infrared spectroscopy to determine the structure of organic molecules. So that's a bit of a mouthful there. So this is very similar in the next point, but solve problems and make predictions. So as it's essentially in this case, make predictions, solve problems are the part that is very important here because mass spec is usually used in combination with infrared spectroscopy for your complex unfamiliar questions, right? So they give you both of those graphs and essentially tell you at the end of the day, here you go, name the compound and then give me the IUPAC name, for example, for the molecule that you've just identified. So generally using both of those to simultaneously to be able to identify a compound, because what does mass spec give? It is just essentially gives you the empirical formula, your structural formula, right? Whereas spectroscopy gives you your functional groups and essentially gives you that specific. So for example, if you have acetic acid, right, so this would be your compound that tells you what actually it is, right? But your mass spec essentially may only give you, for example, your C2H4CO2, right? Sorry, that C is not there. So C2H4O2, which might not give you that much information, right? So using those two in tandem are very important here. So let's first talk about mass spectrometry here, and how the machine works really quickly. So you can see here first step 1, gas sample injection point. So this is where you essentially insert your sample. When it goes into there, you have the sample vaporizer, so it essentially vaporizes it into gas form, right? And why is this important? It's because the mass spectrometer requires the sample to be in gaseous state to be analyzed. So then once it's vaporized, you can see that there's an electron beam down here, and what this does is essentially just knocks the electrons off the molecule. So you're essentially ionizing the molecule here, and this is really important. Two things why this is important. First thing is obviously you have a magnet here. So magnets, only charged particles can be affected by that magnetic field. But also I'll mention about what's its relevance in the graph as well later on. So keep that in mind. Next one, you see that there's two plates here, and these are what we call the accelerating plates. They essentially accelerate the ions that are produced by the electron beam, and they're sped up so they can move through the rest of this machine. So you can see that this acceleration it aligns the ions and pushes them towards that magnetic field. And then when we get to the magnetic field, one of the most important parts of this is when it enters the magnetic field, they are deflected based on their mass to charge ratio. So you guys probably would have covered this already and know it as MZ ratio, right? So essentially this is the most important section because this is where heavier ions, right, with a higher mass to charge ratio, that'll be deflected less to the detector, while the lighter ions, right, with the lower MZ value or ratio will be deflected more. So you can see that this is essentially allows us to separate these ions based on their masses. So this must be a very common concept to you guys now based on your chromatography, electrophoresis and things like that as well. So that is essentially what the detector does. Oh, sorry, the magnetic field does. So the final thing is the detector, what I just mentioned. So it's that essentially records how many of those ions hit at each point on the detector, and then essentially converts that to a mass spectrum graph, that we'll be looking at soon. So we'll see that each peak in the graph, right, corresponds to ions of a particular MZ ratio, and the height of each peak tells us that intensity. So essentially how many ions of that mass were detected. Right, so this is a quick brief summary of the mass spec and how it works. So now we'll quickly go into how to identify and interpret a mass spec graph. So we'll see that one axis will be intensity, one axis, so the x-axis here will be your MZ ratio, right? So first thing we want to do is the identification of the molecular ion peak. So that will be an M plus value here. So what is the molecular ion peak? It's the peak that represents the entire molecule, right? So it's basically the molecular weight of the compound, the whole compound minus the one electron. Remember? So I bring back that minus the one electron because this is what the electron beam does. The electron beam ionizes it, and some people get confused when they see, say, this one here, and then they mention that it's like CH3, CH2, CH3, and there's a plus here for some reason. They're like, why is it plus? Does it mean it's not like complete? No, it's because you have that minus one electron from that electron beam earlier. So this is still the full compound, but it's just ionized, that's all. So for example, if this molecular ion peak is at, say, a 72 value here, what this means is that your essentially your molecular weight is 72 grams per mole. So that's remember, that's your unit for molecular weight. All right, so then the second step is look at the base peak. What does the base peak mean? It's the tallest peak on your spectrum, and this is called the base peak. So what this suggests is it's the most stable and abundant fragment, right? Now, keep in mind, a lot of students get confused by this. It does not always represent the whole molecule. So as you can see, I've drawn here, this wouldn't be considered the whole molecule. But it tells you which fragment is the most common, right, after the molecule is broken apart. So that's why the intensity is the most here, right? So, for example, let's say this is at 43 here. That just means that the fragment that's most stable, the most common, is 43. And you can see it's not the molecular ion peak in this case. Right, so the third one is examine the fragmentation pattern. Now, this is the most important. This is the part that I essentially use personally to really figure out the compound in this case. So what does it mean when I say fragmentation pattern? It's just essentially figuring out the large peaks, like the relatively larger peaks, and then figuring out the difference of the mass to charge ratio between those, because essentially they're the difference in masses, right, between those peaks. And then those masses will correspond, and they'll give you clues, they'll give you hints about what part of the molecule has been lost. Right, for example, we brought in the 72 here. Let's just say you have a peak at 57, right? What is the difference between 72 and 57 in this case? It's 15, right? 72 minus 57 is 15. And this can give you clues, and you'll realize after a while, doing a lot of these mass spectrum graphs, you'll get a pattern of like what certain numbers correspond to what. So 15 is generally associated with this CH3, so a methyl group, right? Because C is 12, and then you've got 3 times 1 hydrogens, which essentially added up together will be 15, right? So you'll notice that 15 generally, associates to a methyl group, and you'll get this pattern of like other certain like functional groups, certain appendages that you'll just notice this is the molecular weight for it, right? So this is the most important part, and you'll get used to it when you do a bit more of the questions for mass spec graphs. Now the final one is check for isotope pattern. The reason why I put a question mark after this is that I have seen questions where they do include isotope patterns, require you to understand it, but it isn't necessarily mentioned in the textbooks, nor is it mentioned in your syllabus. But again, the syllabus is very vague, and textbook may not cover everything. So I'm just going to quickly, briefly mention this because it may not be relevant, but it might be important for you guys to know. So isotope patterns, remember what isotopes are. They're just essentially different versions of the same element, right? So in this case, essentially you'll see these small peaks next to the molecular ion peak, and these are what you call the isotope peaks. So for example, let's just say this is the molecular ion peak, right? You'll see this really tiny peaks here, right? Those are most likely, not always, but these are all sometimes called the isotope peaks. So for example, if you have chlorine or bromine, right, they could have have natural isotopes, and they create those distinct patterns that you see when there's smaller peaks next to it. So for example, chlorine, it has Cl35 and it has Cl37, right? So if your compound contains chlorine, you'll see these two peaks that are separated by 2 mass units, right? So obviously Cl35 will be about 3 times quite a larger peak than Cl37 peak, but you'll see both peaks in the mass spec graph. So I don't want to confuse you guys. I don't want to put too much on you guys. So maybe forget about the isotope pattern. If you're overwhelmed, cover it later maybe, because you guys still have time for the external exam. But if you guys can, keep that in mind just in case. I don't think you will be getting that in the exam, just because they usually just do it with the infrared spectroscopy graph already, so they wouldn't give you that. But yeah, this is essentially the steps that I would take somewhat to answer a mass spec graph. I think the most important thing is just to know. I've done mass spec, I've done infrared spec in university, 3rd year level, and it just comes down to really getting an intuition, getting a vague idea of what's happening, because at the end of the day, these techniques are really to be used together to identify the compound on a whole. Even in university, when we have the high-tech machinery that we use, it's still going to be very vague like this. So it just comes down to doing questions, just making sure you identify that you know what to do, what to cover, what ensures what, essentially to utilize all your information to try and get where you need to be. So okay, let's get into this question here. This is a question or graph rather, taken from the same Oxford textbook. You can see that there's these peaks here, and let's first do the thing where we identify the molecular ion peak. You can see that generally the ion peak here is so 100, 101, 102, 103. So 103. So this guy is at 103. Now your question might be, well, what about this guys, right? That is such tiny amounts. Now you're correct. Those tiny amounts could be the molecular ion peak. However, you'll see that all these three, right? All of these are just in groups, right? Generally, these groups, as I mentioned, could be, those isotope peaks. They could simply be just noise from those H pluses and things like that being broken down. Because at the end of the day, it's essentially a compound being bombarded, being broken down. So there could be a lot of noise in this case, which means that these are most likely noise. So just take the largest one in groups if there's groups like this. So in this case, it's 103, which means that the most likely the full compound is 103 grams per mole. Right? Now we'll look at the base peak. This is the tallest peak, and it's the same thing. This is also the base peak too. So let's identify this as the M plus, but also the base peak as well, right? So this just means that this fragment is the most stable, right, and an most abundant form of it. So knowing that the space peak is the same as the molecular ion peak, what does that actually mean? It doesn't mean too much, but it just means that the compound, most of the compound, is relatively stable as it is, right? So in its full form, not in its fragmented form, right? So now let's look at this fragmentation pattern, and as I mentioned, it's the most important part of the trying to figure out what compound it is, right? So in this case, we've got one at 75, 76, right? So we've got one at 76. Now, these smaller ones might be important later on. We'll check it out. And then 50, so we've got one at 50, possibly 51 maybe, because that's the next biggest one. And here we might have one at like 75, 77 potentially. So let's just take those for example for now, and then let's try and figure out what's happening. So firstly, we can do this two ways. So we can find out the pattern, the difference between these two, so 27, or we could just go off the 76 at the start and try to build a compound from there. But let's start with the 27. So 27, now the biggest thing, as I mentioned before, is to identify what atoms, what elements are involved in this 27, right? So what could make a 27? So remember, we have 15, which could create a methyl group, right? But in this case, 15 and then you have 12, it's unlikely, because it's essentially that would be C2H3 essentially, which wouldn't fit essentially with what we've got here. So what we could do is usually start with the carbon, right? So that's about 12. What do we have left from there? We've got about 15. So 15 could simply be broken up into a metal, as I mentioned, but that's unlikely because you wouldn't have it breaking up separately like that. So that's generally not the case here. So let's say generally we would get a nitrogen here. So nitrogen is roughly 14 to 15. So that could most likely be your functional group here, or your 27 group here, because that is what makes up 27. So this might be something that you guys will be like, what, how did you figure that out? Am I supposed to know that? Again, this comes down to doing a lot of questions, and you'll figure out later on, like 27, what does 27 mean? It's probably a CN group, right? So that's most likely the CN group here that makes up the 27. And then now what's the 77 group or 76 group here in this case? So 76, in order to figure out what and how to make up 76, what I usually do is just firstly get the number of carbons that is closest to that number. So in this case, 6 carbons, because carbon is 12, so that equals to 72. And then what would make up the rest? You would have like 4 essentially hydrogens, of 4 hydrogens, because it's 1, so equals to 4. So you get 76 from there. Now, why did I do that? Because the thing is, let's say you had 11 carbons. So not 11 carbons, 5 carbons, right? What would you get? You'd get a molecular mass of 60, which means you have 16 left to somehow cover. So that's most likely not going to be 16 hydrogens, right? It could be an oxygen, but it's more likely that it is going to be 12 carbons plus a hydrogen, 4 hydrogens in this case. And I'll tell you why. Because of the next fragmentation pattern, but also of how it's come around, right? You'll see that in this you got 4 hydrogens, 6, and you've got a 77 here as well. So which means it's most likely going to be somewhat of a cyclic ring here. So where you have double bonds on your benzene ring, and then you've got, for example, hydrogens coming out here, and you'll see that there's most likely going to be 5 because of the 77 peak, but 4 will just be 4 of them. So, and then this one will be where your extra CN group would attach to. So I understand that this might be like going out of the way in terms of explaining a benzene ring. So, but this is the most likely case in this scenario. So it could be CO. So for example, let's just say C 1 2 3 4, and then 5C, and then O. But again, this is not a molecule. That would be wrong, right? So this would inherently be wrong, because you can't have all these C's without the bonds all attached. So in this case, the most likely scenario is where you have this benzene ring with essentially CN attached here. And then 51, so like you have a roughly 26 difference here. It's essentially just possibly means a smaller fragment, a small hydrocarbon fragment. Most likely, something along the lines of C4H3. So where part of this is broken off, the benzene ring is broken off, and you have, just the 4 carbons, and then the 3 potential 3 hydrogens that are attached to this. So it strongly suggests in this case that it's a benzene ring. And then you can see that there's not any isotope patterns most likely, so creating any of like the isotope peaks here. So from all this information, you can see that there's 103, which suggests which is the full molecule, which is the CN plus the benzene ring, and then the 77, which suggests that breakage of the CN, leaving the benzene ring. So overall, I mean, I don't think you guys need to know this, but it looks like something along the lines of a benzolamine group, which is C6H5, CH2, and H2. So it's essentially the benzyl ring, and then the amine ring here. So that's how you try and figure out from that mass spec graph. Now, this is a more of an advanced one, which is why I used it in this case, because it is more difficult. So don't get like worried or get scared that you're like, wait, hold on, what happened with the nitrogens and the benzene ring? You'll get most likely an easier one than this, but this is the one I looked at in the textbook. It was like it was a hard one, so I was like, let's take this for an example. So generally you won't have things like benzene ring because you guys didn't learn that in grade 12. You guys learned about cyclic structures, but not benzene rings on a whole. So don't get worried too much about that. But that's how you work through a mass spec graph for that. Now you got a second question here. It's not really a question. I just wanted to mention something about this. You can see that in this case we got two exactly same molecular ion peaks, and one of these structures is pentan 2-one, and one of these structures is pentan 3-one, right? So if we just draw these out real quick, so we've got pentan 2-one, which is 1, 2, 3, 4, 5. I'm not going to draw the hydrogens for the sake of time, but then we've got 2-one, which is a carbonyl group, so it's a ketone, right? And then we've got the same structure, right, but we've got it on the second one, so the carbonyl group on there, so the ketone group in the middle. So one of these is pen 2-one, one of these is pentan 3-one. You know, if you wanted to work out if you wanted to work out the actual structure, you could have paused before and trying to figure out yourself, but I've given you the two answers here. But what I'm trying to say is which graph will correspond to which molecule, right? Because at the end of the day, both of these will have the same molecular weight, which is why both of the molecular ions here, sorry, that could go to either one here. Both of these could and do have the same molecular ion peak. So how do we know that which one is which, right? And essentially it's the place where it breaks, right? So for example, in the pentan 2-one, where is it likely to break in this case? You may have a breakage of, for example, so in this case, let's just see you have a difference of 15 here, right? So that's most likely some sort of metal group. But the thing in this case is that you can both break up a metal group here, like that. So then it depends on what's the next one. Next one after that, you've got a 43. Let's see the 43. So what could make up a 43 group here? The 43 group most likely is something like so C36 1 2 3 4 5 6 7. So yeah, so this is most likely the 43 group here, which is not present in the pen 3-one. So where would be the 43 in pentan 3-one? There's not, right? Because this is 12 plus 12 plus 12, which is 36, and then you have the 7 hydrogens that make up the rest of the 7 to make up 43. So this is how you differentiate. And then in this case, you got 29, which is most likely this group, which is your CCs here, which is 24. And then you've got your 5 hydrogens here, which make up your 29. So these differences in the fragmentation pattern, the two different peaks that are occurring, is how you can differ between these two, essentially differ between these two mass spectra. But yeah, so that's essentially how you work out a mass spectrum graph. It's, the question was specifically, as far as I remember, like, what do you need to take in? What peaks do you need to take in? So obviously take out, like, this molecular ion peak that's the highest, but also take the largest peak. So the largest peak is probably one of the best places to start as well, because that's the one that you definitely should take. But the thing is, do a lot of questions. That's the most important thing. So make sure you understand how this works firstly, and then do a lot of questions. So doing a lot of questions, you'll get an intuition of what you need to take into account, what you don't need to take into account. But yeah, so that's how you work out to do mass spectrum and chromatography. So yeah, let me know if you have any more questions.